Welcome to the webinar of today, Sustainable Peak Load Transformer. This is Matteo Troncha from ISGAN Virtual Learning. Before leaving the floor to the speakers, I will introduce ISGAN, which hosts this webinar. ISGAN is the short name for the International Smart Grid Action Network, a technology collaboration program of the International Energy Agency. ISGAN is also an initiative of the Clean Energy Ministerial, formally established in 2011. ISGAN creates a strategic platform to support high-level government attention and action for the accelerated development and deployment of smarter and cleaner electricity grids around the world. ISGAN consists of 27 contracting parties from all over the world, represented in 6 active working groups covering different smart grid topics, from cost-benefit analysis to flexibility markets. ISGAN's vision is to accelerate progress on key aspects of smart grid policy, technology, and investment through voluntary participation by government in projects and programs. ISGAN activities focus on 5 principal areas: policy standards and regulation, finance and business models, technology system development, workforce skill and knowledge, users and consumer engagement. ISGAN facilitates dynamic knowledge sharing, technical assistance, peer review, and project coordination among its contracted parties. The ISGAN value proposition relies on conference and workshops, policy and technology briefs, discussion and technical papers, casebooks, and webinars. Within ISGAN Virtual Learning offers to the community means of rational and continuous technical skill complement and update in the field of smart grids. The Academy is proposed as a set of e-learning and reading core modules dealing with an entire volume share of smart grids. Now it's time to leave the floor to the speakers of the webinar of today, which title is Sustainable Peak Load Transformers. Please use the question and answer tool to pose the questions. The speaker will answer at the end of the presentation. The recording of the webinar will be available in the ISGAN YouTube channel.
So thank you for inviting us to the ISGAN platform, ISGAN Academy. We are 6 authors for this presentation, but there will only be 5 speakers because Phil Hopkinson could not be with us, so his part we will present it for him. I will shortly present, or we will shortly present ourselves, and then we can go on with the presentation. So first, Angelo, the floor is yours to present yourself.
Thank you, Bruno. This is Angelo from University of Bergamo, Italy, currently chair of Cenelec TC14 power transformers. Thank you.
So I think we can go for Alberto now.
Yeah, Alberto Cracco. I'm managing director and owner of Westrafo, Italy. We are a transformer manufacturer, in particular liquid field transformers.
So Bruno de Wachter, I'm a freelance engineer, copywriter, and consultant in the field of electrical energy. And I've been working as an in-house consultant and copywriter for the European Copper Institute since 2011. As Phil Hopkinson could not be with us today, but he is based in the US. He's a life fellow of IEEE and a longtime member of the IEEE Transformer Committee. And he has no less than 56 years of experience in the transformer industry in design, engineering, and management.
Yeah, so at my end, Fernando Nuño from the European Copper Institute. I'm an energy engineer and, in this case, dedicated to the Transformers campaign.
And I am Alan Isbravati. I started my career as a transformer designer. I'm also an engineer. I'm currently the global customers application manager with Cargill, based in Minneapolis, Minnesota, United States.
So Bruno, you can.
I go ahead. Yeah, so this is the agenda of today. We will go in detail later, but I would like to start with a short introduction to the concept of the sustainable peak load transformer. So suppose you have a 400 kVA distribution grid transformer. This 400 kVA maximum peak load limit is there because the maximum temperature rise in the windings is 65 degrees Celsius. This is a limit for the insulation, and this figure has been there already for a very long time. Now suppose that you expect an increase in the peak load of your distribution line, and you want to upgrade this transformer, let's say to 540 kVA. Then there are two options. The conventional option is to just exchange this transformer for a 540 kVA one. Again, this limit is there because of the temperature rise, maximum temperature rise of 65 degrees Celsius in the windings. Now, the second option, and there we come to our subject of today, is to exchange it by a sustainable peak load transformer. This is sometimes also called a dual nameplate transformer because you could say it has two nameplate values. We avoided this name because there is confusion about whether you can have two nameplate values and what it exactly means, a nameplate value. So we prefer the name sustainable peak load transformer. But it has two nameplates, so to say. You have the 540 kVA peak load, which was needed for upgrading this line. But at this peak load, we will have a temperature rise of 95 degrees Celsius. And then there is the normal nameplate, which is 400 kVA, at which there is only a temperature rise of 65 degrees Celsius. What is important, but we will come back to it, that this 95 degrees temperature rise doesn't affect the lifetime of your transformer, the durability. So there are two main reasons why this is an interesting concept. And the first is there, the first I explained already a bit by this introduction, namely, suppose you want to upgrade your distribution line from 400 to 540 kVA, 40 kVA. With a sustainable peak load transformer, the weight and dimensions stay the same. So you can just exchange one transformer for the other one, and you don't need to change anything else. All the foundations and the cabinet and so on can stay the same. So much easier distribution line upgrade. The second interesting aspect of this concept are the material savings. Instead of having a 540 kVA transformer, which is substantially bigger than your 400 kVA one, you will have one of the same dimensions, so lower weight and lower material use than in the conventional one, and this for the same annual energy losses and the similar life cycle cost, and we will come to this later in the presentation. So this is basically the concept. We will now go into details why these are two very interesting advantages. And then we will go into detail of the feasibility. Why can we go to 95 degrees Celsius without affecting lifetime? And why is it not affecting the energy losses? So first, why do we need distribution grid upgrades? This is the part of the presentation that was developed by Phil Hopkinson together with Stephen Rosenstock. You can go ahead, Fernando. So why do we need higher peak capacity? Well, the energy transition is happening. We have the electrification of transport, we have the electrification of buildings, and both are mainly driven by decarbonization policies. And the annual energy outlook of this year by the International Energy Association states very clearly electric loads will increase. So this is a fact. The load on the distribution grids will increase. So electric transportation, it is already booming today, and it will only boom more in the following years. So this is a prospect for the rise of electrical vehicles on the road globally until 2030. We see in blue the full electric vehicles, in purple the hybrid ones, and then in green and yellow, the light commercial vehicles, and then there are buses and trucks. But you see that it will only rise more steeply in the coming years. Building electrification, mainly because of heat pumps for space heating and cooling, and also for hot water. Some countries already oblige heat pumps or don't allow fossil fuel heating anymore for new or innovation, and for instance, Denmark and Switzerland. There are also building automation and control systems which are on the rise, which are mainly there to save energy, but also consume electricity themselves. So it's also an additional load on the electrical grid. And then the communication technology keeps on evolving as well, also electrical. And then there is the domain where where transport and buildings meet each other, and that's in the EV charging stations in buildings. As I said, all this is driven by decarbonization policies. We have clear decarbonization targets in many regions of the world. We have also more and more restrictions on fossil fuel use and infrastructure. There is an increasing share of renewables in the electricity mix, which means that more and more going electrical means decarbonization. And then we have also several countries, an increasing number of countries that have requirements for being EV ready when you build a new building or do a full renovation. So either there must be a charging station already, or at least the connection to make such a charging station must be foreseen, must be there. So to conclude this part, it is clear the load on the distribution grids will increase because of the energy transition. Then the other motivation is material efficiency, and for this part I give the floor to Angelo Baggini from the University of Bergamo.
Thank you, Bruno. Thank you very much. Let's discuss shortly then now the need to take into account in higher material efficiency for power transformers. Let me anticipate that my personal experience is in the power transformer sector is mainly in standardization and regulation. And consequently, let me try to discuss mainly the sustainable peak load transformer subject in this perspective. Let's start from the conclusion. In the context of power transformer sustainability, higher material efficiency is a need in regulation and standardization, at least in my opinion. In fact, the main constraint to go further in power transformer regulation is represented by the availability or unavailability of degrees of freedom. That is, with the transformers standardized as they are now, higher energy performance means larger sizes, larger weights, and higher cost. To be able to go on, I think we have to revise the concept of the transformer itself and or the way to describe, to rate, to standardize it. But let's go in good order. Till now, around the world, as well as in the European Union, power transformers have been regulated mainly in terms of energy performance, as well as other energy related products in EU, in European Union. This has been done in the context of eco-design. The regulation about power transformer is the 548. This has been issued in 2014, and according to plans, it is being amended in 2019. Don't worry, it's the same. Don't worry about slides. Slides are just the background.
That's
yeah,
okay.
No problem. Thank you. Let's say we set up a tier 1 and a tier 2. Now we are close to the next step, that is how to revise this regulation. But the issue we experienced since the beginning in studying and discussing this regulation and the linked standardization has been that power transformer are for sure energy related products, but they are a bit different from the major part of other energy related products like washing machine, TV, and so on. That is relatively few large products with relatively demanding space constraints, relatively few units with relatively high cost, relatively few large manufacturers with in face of relatively few large users. And the power transformer is a mature product standardized in the last, let's say, more or less 100 years, having in mind a series of classic concepts. This generated a large series of exceptions. One of them needed, but I don't like it, is the disproportionate cost and benefits. We cannot manage in this way in a regulation something. By the way, the regulation has been done, they are in place, and we are in front of the revision. One back, please. Thank you. But meanwhile, everything is changed. In looking to the European framework, from the simple willing to be the first neutral climate continent to prioritize electrical energy savings, to develop a power sector based on renewables. Now we added the willing to set up also the circular economy, saving not only energy, but also materials. Please, the next one. In this context, also the standardization bodies, Cenelec for Europe, received the mandate to work on the standardization, not only of energy performances, not energy efficiency as written in this slide, but this is the official one, but also on other new performances of products, in our case, power transformers, like reparability, durability, upgradability, design for disassembly, and so on. That is the next one, please. There is the need in the circular economy to use and reuse the same materials. But as the efficiency of this reuse can never be one, there is also the need to reduce the quantity of used material. This is a clear concept, but in the case of transformer is more tricky than expected. That is, to be able to seriously address this complexity, we cannot stay with this simple concept of transformer we have now. In my opinion, we have to add an additional dimension, that is the usage of the product, or in a more physical way, the time that is not considered now in regulation and standardization. Please, the next one. In fact, we have recognized that our interest is not only in the energy consumption, but in the sustainability as well. And sustainability is material efficiency plus energy performance. In the case of power transformers, energy performance, let's say, has been addressed. Probably we can do more, but addressed. Now we have to address durability, ability to remanufacture, ability to repair, recyclability, recoverability, the proportion of reused components, and this other dimension of transformers. In terms of definition, metrics, limits, test to check if everything is okay. At the time being, with the actual approach for transformer, the link between energy usage and material usage is in fact rigid. We should have to break this rigidity. The regulated, standardized power transformer concept we have now is very simple in principle. Few material used in large quantities, cost and everything the same material, cost and dimension more or less fixed. This because we didn't consider it, we were not in the position to consider the load profile, the usage of the transformer. The extreme example is a spare power transformer, never used. The additional material put in it is unuseful. And then the sizing for the maximum power is something similar. That is better to have something simple, but probably the idea we have now in the standardization of transformer is too simple. Is too simple for our actual needs. Next one, please. And this was the conclusion in the perspective of regulation and standardization, the need of higher material efficiency. And in the perspective of the manufacturer, in my opinion, this is good again. We need, because with the current approach, the added value of the transformer is squeezed by the weight of the material to be used with a limited room for new technologies. Dual nameplate or better peak load transformers could allow an uncoupling of added value for transformer weight. That is, smaller transformer do not mean lower revenue for manufacturer necessarily. The next one, the customer perspective, the user perspective, more or less the same benefit as for the manufacturer, adding that higher peak load capacity for similar dimensions allow we can increase in case of brownfield for the same dimensions the power, and for greenfield we can improve the energy performance. At the end, in one word, in my opinion, we need material efficiency to remove the rigidity we have now in case of our transformer, to multiply the opportunity to reach sustainability considering the usage of transformer. Peak load transformer is something promising in this direction, and is also something that can be considered in the legal framework of European eco-design world that is addressing only manufacturers by juridic reason. The real criticism now will be on how to standardize and regulate it. Thank you.
Thank you very much, Angelo. So we need material efficiency. There's a rising concern about this. We also need to upgrade the peak capacity of our grid. And the sustainable peak load transformer is an ideal concept to combine both advantages. But how do we make this happen? What is actually the technology behind this? And for this, I would like to give the floor to Alan Sbravati. Alan, go
Thank
on.
you. Thank you, Bruno. Yep. So the magic here, which is absolutely not a magic, is the interaction between the natural esters, vegetable-based oils, with the also natural cellulose-based paper. So when the natural esters were developed, they were focused on fire safety and environmental performance. But during the validation or the confirmation of the long-term performance of the transformers, Cooper Power Systems, who developed this solution, found out that the interaction between the natural ester and the paper was different than that of mineral oil and paper. And the degradation rate of the paper was dramatically reduced. So it's 7.4 times lower. The result of this is a possible increase of 20 degrees in the thermal class for the very same paper. So you see here in the screen, aging side by side. This is a high temperature aging at 170 degrees. And you see that after 1,000 hours, the paper that was aged in mineral oil is already very brittle and black and very fragile. And even after 4,000 hours, the paper that was aged in FO3 fluid, in a natural ester, was still brown and almost looking like the mineral oil, paper immersed in mineral oil after 500 hours. If you could move to the next. Then they started investigating what is behind it. Fernando, if you could move to the next slide, please. Yeah. And the reason is all about water. We know that when cellulose degrades, it generates as a byproduct water. And this water remains impregnated in the paper, generating more degradation. And then more degradation generates more water that generates more degradation. This is what happened when the paper is immersed in mineral oil. Conversely, when the paper is immersed in natural ester, the water that is generated by the paper degradation migrates to the paper and to the oil and is consumed by the natural ester. So the result is what you see here in the screen. The comparison that you saw is exactly this. When you reach end of life for the paper immersed in mineral oil, you only consumed 16% of the useful life for the paper immersed in a natural ester. And on top of that, the paper is drier. And a drier insulating system is a better dielectric. So you don't compromise the reliability of your transformer after years of operation. If you could move to the next, Fernando. And here we see more in detail what happens. Natural ester has a higher saturation point, so water migrates to the oil, and then the water is effectively consumed by the oil. So the water will not migrate back to the paper when temperature decreases, because there is a hydrolysis reaction where the water is broken into hydrogen and hydroxyl, and then the hydrogen connects one side, hydroxyl forms a long chain free fatty acid. So you see as a type of degradation that the acid content in the natural ester will start increasing. But these acids, instead of attacking the paper and promoting more degradation, they actually combine with the cellulose molecule, and this is the transesterification, and they protect the paper. If you could move to next, Fernando, please. When you bring this to the transformer perspective, you have the transformer designed to the same 65 Kelvin average winding rise, traditional, all in all standards, and this is the brownfield solution that Angelo was presenting. But if you have a transformer with mineral oil designed to 65, nominal life happens at the same point of 65. When you have the transformer designed to 65 and you are using a natural ester, the nominal life will only happen at 95, 30 degrees more. Why 30 degrees? Because there are 10 degrees on the difference between kraft paper and thermal upgraded, and 20 degrees on the thermal upgraded in mineral oil versus the thermal upgraded in natural ester. So the effective continuous loading capacity would be when the average winding rise reaches 95 Kelvin instead of 65. So you have 30 degrees more to increase the loading capacity without reducing life. And on top of that, you have the red region, which would be the overloading with additional life consumption, which is also larger because the maximum top oil temperature you can have on a natural Westerfield transformer is also much higher than that of mineral oil, 140 instead of 110. If you could click one more time, Fernando. The other dimension that we will check is life expectation of the transformer. So since you will be running the transformer most of the time around the 65 Kelvin, you will have a longer life in a natural Westerfield unit in comparison to the mineral oil unit, even if you use this higher loading capacity as a normal loading condition, right? One more time, please. And also, there is the aspect of reducing the degradation rate or the likelihood of a dielectric failure for keeping the insulating system drier throughout the life. Then when we talk about the purchase cost, when we have the same size, designed to the same temperaturized limits, we would expect a little bit higher initial cost, right? But this would be by far compensated by the increased loading capacity. If you go in the other direction, as Angelo presented in the greenfield, we would have a more compact transformer with lower usage of materials and potentially even cheaper. The important point here is, as Angelo mentioned, the losses and the assessment of the losses in the transformer life considers nominal rated capacity, but the transformer is static, as Angelo said, but the transformer is always dynamically loaded, and a typical average loading will be much lower than 100%. So when we expand the loading capacity, we can increase the average loading, increasing the asset utilization, and bring this closer to the sweet spot, which would be a 50% average loading. That was my portion here. Thanks a lot.
Thank you, Alan, for clarifying this. So the sustainable peak load transformer can withstand those higher temperatures without affecting lifetime. But what about the energy performance? Because material savings is clearly getting more and more attention, but it doesn't mean that energy efficiency is less of a concern. On the contrary. So Fernando, for this chapter, I give the floor to you.
Great, thank you, Bruno. So indeed, let's have a look at this. So for this, we have prepared here the graphs for a conventional unit, which uses, which is sized as in the example before 540 kVA, and then dual nameplate or sustainable peak unit, which is rated to 400 at 65 degrees, but 532 at 95 degrees. So basically, in terms of peak load capacity, both are comparable. If we represent in this graph the limits imposed by the European regulation, we have the core losses. For this, we have represented in blue the core losses. Then this unit would be compliant with it, and also binding losses. And this is the limit in green here. Let me maybe put the pointer. Yeah, so here, so this unit, the conventional unit, of course, complies with the regulation. If we look at the reduced size unit, then the nominal, or the base nameplate is 400 kVA. And then if we represent in yellow the limits established for core losses and winding losses, we see that this unit is compliant with both. But of course, if we represent in gray the winding losses at 95 degrees Celsius rise, of course, these are much bigger. So these are well beyond either the 400 regulation or the 540 regulation. So we could say, wow, this unit is not really fit for the European regulation. But actually, what we should care about is the total energy losses on annual basis. So for low loading of distribution networks, so the low loading of distribution networks leads to core losses dominating the annual balance. So as we can see here in blue, these are core losses, and this is what dominates the annual balance. So what matters is to reduce core losses, to reduce more core losses than winding losses. So a reduction in size leads to lower core losses, as we can see here. Of course, such reduction in size leads to higher winding losses here. But overall, what we can see is that the reduction in core losses is bigger than the increase in winding losses. So on an annual basis, the energy performance remains equal or slightly improved. And this is actually what matters. So how much absolute energy is consumed, not theoretical points on the transformer. So significant savings. So the advantage of the second design, so the more compact design, is okay. Energy-wise, it's quite the same, but then the advantage is material use. So we are seeing that in the next slide. So if we represent here the amount of steel consumed by these two units, which are equivalent in peak load and equivalent in energy performance, we see that steel is reduced by 20%. We have used a design which has aluminum coil and copper coil. So for low voltage and high voltage. So the reduction in these two materials is around 20% as well. And the consumption or the need for oil is reduced by 16%. So overall, the advantage is that for the same energy performance, the same peak capacity, less material is used. So how do this compare? So we represent here the no load losses and the winding losses of a conventional unit. Then we represent the sustainable peak load unit, which is smaller, so the core losses are lower, the winding losses are higher. And then there is a point where loss is equal. So all the issue with these technologies to know whether we are behind or beyond this tipping point in terms of loading, more notably in terms of average loading. So the question is whether distribution transformers are indeed in this region where the green line remains below the gray line, and not here where, of course, it wouldn't make sense because it's of course, from an energy point of view, it's less convenient. So let's indeed see what the surveys show here. And then the question is whether this average load in distribution transformer, distribution grids is low enough. So whether we are in this region where indeed the smaller transformer makes more sense. So here we will present a survey carried out by Dan Mulkey, which is IEEE Life member for 2 years experience. And basically the analysis he carried out is as follows. He measured over more than 60,000 transformers in East Coast of US, their behavior, so in 15 minutes data points, so a huge amount of data points over more than 1 year. And then he prepared this root mean square average over nameplate capacity. So basically these points give us what's the average loading, whether it's 16%, 72%, 100%, oops, sorry. Not yet here, etc. So what he found is that the mode, so the most repeated value, is 0.13. So this means that average loads of transformers there distribution transformers is as low as 13%. And actually, the bulk of the situations is between 6% load and 25% load. So this confirms that by large, distribution transformers are very poorly loaded. Of course, they have to be sized for peak situations, but actually this happens very rarely in time. Actually, some transformers, very few, reach average loads of 50%, which is the optimal, as Alan said before. So that's the situation. If we go if we focus on strictly residential customers, because here, well, it's all kind of customers, so residential, tertiary, industrial. Here, well, the findings are quite the same. So 12% average load, and typically ranging from 6 to 24%. So it's quite the same finding. So the key findings of the survey, well, starting from the nameplate, which would be 100% capacity, what is found is that peak demand is as an average only at 45–55% of nameplate capacity, and average load at 12%, 13% load. So this means that indeed we are well in the left side of the curve that we mentioned before. So we can expect similar order of magnitude of loading in Europe. So as Alan commented before, for several transformer designs of several nameplate capacities, so 17, 22, etc., up to 118, the best efficiency occurs at roughly 50% of the load. As you can see here, for the various designs, this is where it happens. So increasing a transformer peak capacity for the same nameplate rating allows expanding the use range of the units. And as the optimum is around this 50%, with this sustainable peak transformer, we are tapping higher in average load. So we are not at the 12%, which is pretty low, and efficiency is also quite low, but rather at higher loads where the efficiency is better. So there is double gain. Good. So I think that's it for this part. I will continue on a modeling exercise which has been carried out for Europe. So basically, the question that we asked here is, well, we start from a certain MVA, so megavolt amp, installed capacity in Europe in starting point 2020. This fleet of distribution transformers, of course, has to be renovated, replaced, because end of life progressively. So the existing fleet goes down up to 2050 in that way. The rhythm of substitution is the same as assumed by the European Commission in its preparatory studies. And then, of course, loads are expected to grow, as previously said by Bruno, because of electrification and energy transition. So the question is, what if these new transformers coming here to replace old ones and to fill for the load increase? What would happen if we, instead of using conventional units, we use sustainable peak units? What would be the gains in terms of energy performance and in terms of energy efficiency? So let's see that. So as mentioned, we have extracted from the EU Green Deal impact assessment documents the expected growth of electricity consumption in various segments. So in the service sector, not so much. In industry, we can see an acceleration towards 2050. So the three columns represent 2015, 2030, and 2050. In residential, the acceleration would take place rather up to 2030, and in transport, the clear growth in the years to come. So overall, if we represent the total amount, we can see how the electricity demand will evolve from 2,500 terawatt hours per year, roughly, to near 3,500, so a 30% increase, roughly. So based on this, we have estimated the distribution transformer load. So as mentioned before, well, with more electrification, there will be more terawatt hours per year, which will need to be transformed in distribution transformers. Some load pattern assumptions. So based on the findings of the survey before and based also on the preparatory studies by the European Commission so far, we have defined certain load profiles, then with certain average load and root mean square loads. And based on this, we have represented both what we have already discussed, so the existing fleet in gray and the new fleet. So what happens in the first scenario, which is conventional transformers replacing the existing fleet? So the existing fleet goes here. There is a share between core losses and winding losses. And the new fleet is in the lighter color, also with core losses and winding losses. So this is the way losses evolve. Despite the increase of loads, losses reduced because of the eco-design regulation requiring, well, more efficient units. So overall, losses would reduce. But then let's see what happens if we replace these old transformers with sustainable peak transformers. Actually, the shape of the curve is quite the same. We have less core losses in exchange of more winding losses, but overall it's quite the same. Actually, let's see that in a combined slide. So we have the conventional units here in light gray, and then the sustainable peak units in green. So what we find is that actually the level of total losses remains the same. We have simply shifted more core losses for less core losses and a bit more winding losses. So the question is, does it make sense? Why would we do that? Well, as said before, we would do that to save material. So basically, we'll be saving 20% in active materials, 15% less weight, and cost, we put here 9% less. This can be discussed because, of course, costs is a different, depends on the prices of all these materials. What is a fact is the reduction in these amounts. So we would be talking about 16 kilotons per year saved steel, 3 aluminium, 7 copper, some oil, etc. So that's it. I will now give the floor to Alberto. Bruno, I don't know whether you expected to make some introduction here.
No, well, thank you, Fernando. We will go give the floor to Alberto for an example from the field, because those transformers are already being used today. Alberto, the floor is yours.
Yeah. Thank you, Bruno. Thank you, Fernando. So the question that are usually coming from the utility and the end user to the OEM is, how mature is this technology, and does exist any transformer that fits the SPL concept that we just see? The best answer that we can provide as OEM is to show a couple of samples of projects that we have done with some utilities in Europe. And we will start with one case that we did with Vattenfall, with Stromnetz Berlin, where we have done a project where we deliver to this utility 10 transformer SPL type, 630 kVA as nominal power, 800 kVA as SPL power. So what we have done with the utility was to define what was the scope of the supply, and in particular to define what was the test that has to be carried on this transformer in order to show that we can meet the norms and the regulation that are described by the utility. So if you go to the next slide, I want to show you that without entering into the details about the design of the transformer, we can see that the SPL design concept, as we already see with Fernando and Bruno before, has a reduced footprint of the transformer itself compared with the normal transformer that are usually used in the network, has no losses that are sensitive lower than the standard transformer, that mineral alloy transformer that are usually used. And as a consequence, we have the possibility to use this transformer with a bigger power in existing substation without entering in civil and construction works. So this is a big advantages for the utilities that need to do an upgrade of the network in the city center in particular, or in the existing network distribution network. But if we go to the next slide, the thing is why this project is so interesting as an OEM for us. It was interesting because we did several tests on this project. We performed several different customization for the project to meet the requirement of the utility and the technicians of the utility that want to test this type of technology. So first of all, we produced a transformer respecting 100% the technical specification that was provided by Vattenfall, and we perform all the type tests, routine tests, and special tests that are usually requested by the utility, as for example, temperature rise test as the SPL power, checking that the over temperature of the transformer are respecting the IEC 7614 norms limit that are provided. We performed a noise level test. One bigger advantages of this type of transformer is even the reduced noise compared with the standard transformer due to the reduced no-load losses that it can generate. And for sure, we performed even short circuit resistance test with full inspection after the test that was executed in chassis. Obviously, all these tests that we perform were performed by the manufacturer in a external laboratory and were successfully, and the transformer were accepted by the customer. Moreover, if we go to the next slide, please, the OEM and the customer want to do some additional tests during the lifetime of the transformer. In the preliminary phase, before to enter in a contract with a utility, we agreed on a way that we have to test the transformer insulation material that we use for manufacturing the windings during the lifetime of the transformer. In order to do that, we define a special pocket inside the windings where we install some samples of paper and material that could be extracted by the utility during the lifetime of the transformer itself. This procedure was agreed, obviously, between the quality guys of the utility and the engineers that designed this transformer. Following this method, every 6 months, the utility has the opportunity to inspect the windings, to inspect the active part of the transformer, and verify if there is a decomposition of the insulation material. After 4 years, we can say that at the moment there is no any decomposition. The material is still perfect, and the DGAs are still showing perfect values compared with the starting value. We can even see another project that we did in the next slide, where we have done a second project that is a comparison between a standard 400 kVA transformer delivered by one of our competitor in a German utility company. And on the side of this transformer, there is a Westrafo transformer, SPL design, with the same footprint, same dimension, was installed inside the same substation. And as I said before, this is a big opportunity for the utility to reuse the existing substation without doing civil works and having an increment of the power rating that is available in the substation. Here we push to the extreme the concept of the SPL, and we had a bigger overload of 55% compared with the nominal power. This was a test that the utility want to perform, and we can see in the next slide that the utility are using this transformer at a sustainable peak load during the lifetime of the transformer. As we can see in the diagram, we have during 1 year in 2018, we have a continuous load during the day of 600 kVA with compared with the 400 kVA as a nominal power of the transformer. So this is exactly how the sustainable peak load can work, and the utility is testing the transformer not only as a duty cycle, but even has the composition inside the material and lifetime of the transformer, performing DGA's analysis continuously every year for monitoring the status of the transformer. Obviously, after 4 years, if we are here speaking about this case, that the transformer is still running in a perfect way, and the customer is very satisfied about this. So coming back to the first question, how mature is this technology? We can say that this technology is mature enough to be used without any fear from the utility and from the customer, and so it has not to be looked with suspicion from the technicians of the users usually. So with this slide, I complete my presentation. So I pass the microphone to Bruno that can go ahead.
Thank you, Alberto. So after this, we will conclude with a short wrap-up of our entire presentation. So the average loads in distribution grids are low. Measurement campaigns have proven that they are even lower than we thought before. And this means that the load in a classical distribution grid is within the field where it makes sense to use a sustainable peak load transformer, namely the field where the no load losses are dominant on the load losses. Next slide, please. There are two main advantages of this concept. First one is a capacity upgrade of around 30% that is possible without increasing the dimensions or the weight of the transformer. So transformers can just be exchanged and increase their peak load without any further changes to the site. The second big advantage, which is an increasing concern in many regulatory instances around the world, material savings. And here we see that for the same peak load capacity, we have a smaller transformer and consequently also much less material use, and this for similar annual energy losses and a similar life cycle cost.
Yeah, here I would say even, sorry, Bruno, that, well, Alberto has just shown how capacity upgrade in that particular case went up to 55%. So this is at least 30%, if we can say.
Indeed, at least 30%. Thank you, Fernando, for this adjustment. And then, so as said, the material savings are substantial, and this has been shown by a modeling exercise for the EU. If all replacements of distribution transformers would from now on go to a sustainable peak load transformer, we would save 16 kiloton of steel per year, 3 kilotons of aluminium, and 7 kilotons of copper. And we would also save oil, and there would be a reduction in 9% of material costs. And all this with a proven technology, which is available on the market and which has been tested in many cases, both in Europe and in the US and in South America. So the technology is there to be used. Thank you. That was it for today. So now we go to the question and answer chapter. Have there been any questions, Matteo?
Yes, thank you for presenting the webinar. Yes, we have questions. Questions are arriving. I don't know if you can see the question answer tool, and I can read the first question. And so the audience asks if there is any incompatibility from the current EU regulations with the SPL concept to be used in distribution grids.
Well, I think this refers to my section. So I wouldn't call it incompatibility, but needs a clarification, because indeed the sustainable peak load transformer can indeed comply with the lower rating limits. So basically with the 65 degrees Celsius temperature increase, but when it runs at higher in temperature and load, then of course winding losses become bigger, and it would require an extra sizing of the windings to keep within the regulation. So indeed this needs clarification, because at the end of the day both concepts can deliver the same amount of annual energy losses. But indeed, that's something that needs to be discussed with policymakers. I don't know whether other Angelo is more related, or Alberto, do you want to complete?
Yes, please. I am with you. That is sustainable peak load transformers for the time being are not recognized as something different. So if they are considered with the actual metric, they are fully in line with the regulation, but considering them with the actual metric does not put in evidence their additional characteristics.
Yeah, and the testing reports were certified by Chassis, so it's all compliant with the eco design and all of that, as Alberto showed in his portion here.
Yeah, I want to add that usually there is some confusion inside the regulation, how to make interpretation about the regulation for these transformers. So from one side, there is a commitment from the customer, from the user and the utility and the producer. From the other side, there is how we are defining the sustainable peak load transformer on the nameplate of the transformer itself. And what he has to be clear is that this is there is a sustainable peak load transformer that in the nominal power is respecting the eco design regulation usually, and the SPL power is a deviation from the eco design regulation, and this has to be accepted and certified.
Good. So maybe we can, Matteo, go ahead.
Yes. Okay, thank you for answering. Okay, I can move to the second question. And okay, maybe it's not a direct question. They are asking you to think about the impact of new load like electric vehicles to peak load transformers.
Maybe I can do a comment on that one. And, you know, the perception of this typical average low or low average loading in the transformers indeed indicates that there is a reserve of capacity in the existing grid. But the additional load of the electrical vehicles will increase a lot. We are replacing the gasoline in the fields by electricity, and this will increase, based on another study from Edison Institute, it would represent something around a 35% increase on the energy consumption in 1 year. But we know that the peak amplifies the average increase by a factor of 4. So we are saying that if the average increase is 35, the peak will increase 140%, and then it will exceed the capacity of the existing transformers. So the reserve of capacity will not be enough for the additional loading from the EVs.
Okay, thank you, Alan, for clarifying this. Next question from Mr. Kai Polari. In comparison, the load losses. In the comparison of the load losses between the two alternatives, which reference temperature you used for the sustainable peak load instead of 75 degrees Celsius? Maybe Alan, you can also answer this one.
Yeah, and that's an important clarification. So we are not changing the rated capacity of a transformer. So transformer, as Alberto showed it, transformer was still rated 630 kVA at 65 rides. On top of that, the transformer has a beyond nameplate loading capacity, which can be a continuous loading condition of 800 kVA. So for the losses, for the evaluation, according to eco-design, you won't be changing the temperature reference for losses because rated capacity remains at the same temperature.
Thank you, Alan, for clarifying. And there is a second question in the same field or close to this. How suitable are sustainable peak load transformers for tropical countries like India, where ambient temperatures reach 45 degrees Celsius?
Copper, natural ester, they love high temperature, so it will be much better and work perfectly. Maybe Alberto is laughing here. Yeah, you can compliment.
Yeah, I agree with you.
Yeah.
There is no discrimination about the ambient temperature for designing an SPL design transformer. So if 40 degrees, 45 or 50 degrees, the engineer can design an SPL transformer based on the ambient temperature that is referred to the local conditions. So that's is not a limitation.
Thank you, Alan and Alberta, for clarifying this. Next question is from Mr. Pete Osterle. Have you considered to use Nomex insulation material, and if so, what was the conclusion not to use it? I think, Alan, I have to turn to you again for this question.
Nomex is another alternative, and there are, especially when you need very compact transformers, it is the way to go. But the question is on the cost side, because it will add some additional cost on the insulating material. Maybe Alberto can comment this a little further. Yeah.
Yeah, the norm doesn't describe which type of material we need to use. Nomex is for sure one of the producer through the Corning of this high temperature material that we can use in the insulation, but obviously has a counterpart, a higher cost compared with the standard temporal upgrade paper material or higher thermal class material that we can use. So is a choice of engineer to define which type of material, and we cannot be limited to use only one type of insulation material in the designing of the transformer. So Nomex, to answer to the question, is considered, but is considered only in particular cases.
Thank you, Alberto and Alan. And maybe to finalize all the questions about the material, there is a question about revenue 1 on special requirements for gasket and accessoires selection, like higher thermal class. How does this affect the overall material cost of the sustainable peak load transformer? Alberto or Alan?
I think I can answer to this question. Obviously, the design of this type of transformer is considering different type of material compared with a mineral alloy standard transformer. That means a gasket, that means insulation material, that means even accessories that can work at higher temperature inside the we install in the transformers. Coming to the cost, the design of this transformer has the target to not increase the cost, so to be comparable with the actual transformer that are usually installed, despite the fact that we have a higher capacity available for this type of transformer. And this is the target of SPL concept, I think. And we see before, Bruno, with your presentation, with the Fernando presentation, that we are using less material to design the transformer compared with the mineral alloy standard transformer. And this is creating a cost benefit in designing this type.
Indeed, thank you, Alberto. So costs might go up for some materials, but then they go down for others, and the overall cost stays more or less similar. And there is a question from Michel Sacot. Have you launched some revision of the regulation or standardization to keep compliant these transformers with the standards and regulation? There I would turn to Fernando or Angelo. Would one of you like to answer this question?
Yeah, no problem. The answer is not yet, but we have started to communicate about the concept. And our idea is indeed to share also with the regulators. There is expected a revision of the regulation in Europe by July 2023, so 1 year from now. So this is likely to be part of the discussion meanwhile. Angelo, maybe you want
no, nothing more. Not yet. In my idea, it would be nice to be able to consider also this new concept in the regulation and in the linked standardization, for sure. But not yet.
I'd like to add to that, Angelo. As you mentioned, the eco design considers a static condition, rated capacity.
Yeah.
So adding this dynamic or the time axis or aspect in the standard would help a lot. But it's important to clarify that there is no need to change the standard right now, and that the transformers are for the transformers to be used, that the transformers, according to the concept, they comply with the existing standards. Yeah, so there is a lot of opportunity to improve and to make that more beneficial for the market, but they are not going. There is no conflict between the solution and the current standard, right?
Thank you, Fernando and Angelo, for asking this question. And with this, I think we have answered all the questions that were there in the Q&A too. With this, I give the floor to you again, Matteo. Thank you.
Thank you to all the speakers. And I don't know if you wish to have a final remark before closing the webinar.
Okay, so well, I think first we would like to thank ISGAN for accepting our proposal to communicate on these sustainable peak load transformers, and we would be happy receiving any inquiry, any question from the audience. Do not hesitate through Matteo or through the names which will appear in the last page of our slides. To go back to us. Alan?
Yep, so also thanks a lot for the opportunity. I think that is great when we bring a lot of different viewpoints together. So it was a pleasure joining the webinar.
Angelo?
Thank you for the opportunity also from my side. This is, among others, a disruptive idea. We have to discuss a lot, and this was a great opportunity. Thank you.
Alberto?
Yeah, it was a great opportunity even for me to show some example of this technology that personally, as with our company, we are investing on this technology since 2016. So it's almost 6 years that we are delivering to the market this type of transformers, and we see that the demand is growing and growing every year, and this is only a good opportunity, I think, for all OEM in the world.
Bruno?
Thank you for to all the speakers, and thank you to all the participants for showing your interest and for posing interesting questions. And above all, I would like to thank again the ISGAN Academy for inviting us to discuss this topic. And have a nice rest of the day.